All right. Hi, everybody. Me again. Today, we're going to be talking about limiting reactants and percent yield. Before we do that, I'm going to go ahead and do one stoichiometry review problem. So to do the stoichiometry review problem, you might want to try doing it with me. Maybe grab a paper and pencil and a calculator, see if you can keep up with me. I'll do it over on this squid program here that I can write. I'm going to just write directly on my Chromebook, so I might look a little bit funny as I'm writing. Okay, so it says how many grams of KO2 are needed to form 7.5 grams of O2. So we have, in this case, we're given the 7.5 grams of O2, so that's what I'm going to start with. And I'm going to choose a better color than brown. I'm not a huge fan of brown. So I'm going to write down 7.5 grams of O2. Sorry about my messy handwriting. I'm going to draw my first conversion factor. I have no idea what I'm doing right now, but I know that grams of O2 is going to go on the bottom so that they cancel out. So then it looks like, and I remembered my handy dandy periodic table today. So it looks like we're going to try to get over 2 grams of potassium oxide over there. So the way that I'm going to make this work, let's figure out how many grams of oxygen there are in 1 mole of oxygen. So I'm going to start like this. And I'm going to look over at oxygen, and oxygen is 15.999. We could round that to 16 tonight, times 2. So there's 2 of them because it's O2. So we're going to say 32. That really should have a couple zeros after it. There we go. Just if we're talking about sig figs. Okay, and then that was 1 mole of oxygen, and that allowed us to cancel off one of our units. And now we're going to continue with our conversion factors. Now we know we want moles of oxygen on the bottom to get them to go away. And this is where we're going to use our mole to mole ratio. So I see that for every 3 moles of oxygen, we need 4 moles of KO2. Oops, I should have written mole there. There we go. And that allows my units to cancel for moles of oxygen. So now I'm in moles of KO2. And last, I'm going to convert that, wrong color. I'm going to convert that into grams for our final answer. So we know in 1 mole of KO2, we have how many grams? And I better look that up. So let's see. Potassium is 39.102 plus, and then in parentheses, 15.999 times 2, close parentheses, is 71.1 is my mass of 1 mole of KO2. And now I see that my units have fortunately canceled, and I am left with the unit that I was looking for. So now I'm going to multiply everything. So the things that I need to multiply, I'm going to circle. I need to underline 7.5 times 1 times 4 times 71.1 divided by, and then in parentheses, 32 times 3. And that will give me my final answer. So I'm going to do that right now. So 7.5 times 4 times 71.1 divided by parentheses 32 times 3, close parentheses, 22.21875. I'm going to look at my initial number of significant figures, which is 3 today. So I'm going to take that to 22.2. And that, ladies and gentlemen, is our review stoichiometry problem. Now, stoichiometry is the foundation for all the other things that we're going to do, including what we're going to work on today, which is called limiting reactants. So I'm going to go back to my presentation. And we will talk about limiting reactants. So we have this great analogy. I mentioned this analogy, I think on the stoichiometry presentation, but I'll take it into a little bit more depth here. When you have a recipe and you have ingredients, there's at some point in the amount of ingredients you have, there's a limit to how many of the products you can make, how many of the food items, whatever it is. So in this case, we're trying to make a pizza. And the question is, how many pizzas can we make? We have 1 piece pizza crust. We have tons and tons of cheese and tons of sauce. So the question is, how many pizzas can we make? Well, the answer is pretty obvious. We only have one crust, so we're only going to make one pizza, and we'll have cheese and we'll have sauce left over, but all we get to make is one pizza. And in that case, we would say that the pizza crust is limiting how many pizzas we're allowed to make. So up to this point in problems that we've had for this class, we've always given you the correct amount of ingredients, correct amount of reactants to produce the correct amount of product. Well, this time we're going to start messing with the ingredients. If we give you a little bit of this and a little bit of that, how much of the product are you going to get? And then on top of it, you're going to have to factor in laboratory error, that not all reactions run to completion. There's often errors in measurements and in the equipment. So we're going to calculate also percent yield. We'll be able to predict how much you should get, how much product you should get. And then we're going to look at, okay, did you actually get that much product? And if not, what percent did you get? All right, so let's take a look. Let's try this first problem. A definition, I guess, first. So limiting reactant is the reactant that runs out first, therefore stopping the reaction. In our example of the pizza, it was the pizza crust that was the limiting reactant. To determine the limiting reactant, we do Stoich problems. So that's why we just did that practice problem. For each reactant, so you do a stoichiometry problem for the pizza crust, you do a stoichiometry problem for the cheese, and you do a stoichiometry problem for the sauce. And then whichever one produces the least amount of product, that's your limiting factor. Well, with the pizza crust, the one that produced the least amount of product was the crust. And so we could say that that's our limiting reactant. All right, so here's an example problem. It says how many moles of the product are made when we have 4.5 grams of hydrogen and 64 grams of oxygen that react. Well, the first part we need, I kind of like this unit. I find stoichiometry problems extremely satisfying. Once you get the hang of them, like they're tons of writing, but once you get the hang of them, the crossing off of all the units, I find pleasing. But what I like about this unit is that it pulls absolutely everything we've been talking about together into one thing. So you have a reaction here. At times, you're going to have to write the reaction yourself. You're going to have to figure out what the reaction is. Then you have to balance the reaction. You have to make sure that you've got the correct coefficients. Then you have to do stoichiometry. Then you have to figure out what the limiting reactant is. Then you have to figure out whether you got the appropriate percent yield or what percent yield you got. So in this case, we have our balanced equation, and it shows that we have a 2 to 1 to 2 mole ratio. So it says, in order to solve the question, it says, do 2 stoichiometry problems. The first one, we're going to find out how much water does the hydrogen produce. In other words, if you just had 4.5 grams of hydrogen and an unlimited amount of oxygen, how much water would be produced in that circumstance? And then you're going to do it the opposite way. If you had only 64 grams of oxygen and an unlimited amount of hydrogen, how much water would be produced? The one that produces the smallest amount is going to be our limiting reactant, and that will be the right answer then. The smallest amount is always going to be the right answer. So let me give you an example. Now, I will say right here that the person who set up this presentation, which it wasn't me, set them up in columns so that you could compare them side by side. That feels awkward to me because I always do stoichiometry problems horizontally. So bear with me while we look at this. But so they've put 4.5 grams of hydrogen on the left and 64 grams of oxygen on the right. So the first thing that we need to do is to convert both of those into moles. So you see how much is in 1 mole. We've got the atomic mass underneath, and that crosses out the grams and leaves us with moles. Fee-fed lifting. And then we need to do the mole to mole ratios. And that will give us the amount of the product. So on the left, we see that we produce 2.3 moles of water with the amount of hydrogen that we were given. And on the right, we see we produced 4 moles of water. So which one was the limiting reactant and which one is the correct amount that we would actually produce? Well, the 2.3 moles is the one that we would actually produce because we will have run out of hydrogen. So that means hydrogen was the limiting reactant. And that means that the oxygen is the excess reactant. It means we have it left over at the end of the problem. All right, so now we want to see if we've produced a good amount of water. You almost never in the laboratory produce 100% of the product. It says here, all stoichiometry calculations are theoretical. Theoretically, this is how much water you should produce. How much did you actually produce when you were in the laboratory? So it says lab reality implies something happening, some sort of error, like a bad filtering apparatus, some spilling, Mr. Williamson, whatever, something getting in the way of us getting 100% yield. So the percent yield is a measurement of the efficiency of reaction, and percent yield is really simple to calculate. So here's example number 2. Let's say the reaction from the previous problem runs with an 80% yield. How many grams of water actually produced? Well, 2.3, and it says how many grams of water. We were in moles of water initially. So let's do the 80% right off the bat. 2.3 times 0.8 gives us the number of moles that we actually produced in the lab. And then we need to convert that into grams using the grams to mole ratio. And it comes up to 32 grams, and that's how much we produce. So remember that the 32 grams reflects the limiting reactant, which was hydrogen. Hydrogen only allowed us to produce 2.3 moles of water. Then we only produced 80% of what we were supposed to produce, so we only got 1.8 moles of water. And then we had to convert that into grams. Okay, so that's it for this particular presentation. I did want to take a minute, and you can skip this if you want, but I did want to take a minute and see if I could, give me a second to get organized, see if I could go through with you one problem from our limiting reactants worksheet. So I'll walk you through this first problem. Hopefully I'll be able to do it without too much trouble. And then you're free to do these problems on your own or with a buddy. I never mind you doing it with a buddy. Let me say that I do expect you, however, to be doing this by hand. I'm getting kind of irritated with some of my other classes that are turning in copy and pasted work for me. So I need to see your handwriting on this. Whether you do it on a piece of paper and upload it for me or whether you use Cami to do it, I don't care. Okay, so let's start out. It says a sample of 0.610 moles of copper 2 sulfide is treated with 1.4 moles of nitric acid. The reaction is shown below. So there we go. I will warn you that in the future, they don't give you the reactions. So on problem number 2, they tell you it's a double replacement reaction. You have to figure that out, right? Okay, so it says how many moles of copper 2 nitrate could be produced? So let's try that right off the bat. So the first thing we're going to do is write down each of the reactants. So how much would we produce if we had 0.610 moles of copper 2 sulfide, and how much? Sorry, I'm reading it incorrectly. I was thinking that was the product. So sorry, I had to read that really carefully. And how much would be produced if we had 1.4 moles of the nitric acid? How much of this? That's what we're trying to figure out. How much of that would we produce? So let's do the first one first. So let's do the 0.610. I'm going to flatten this so my screen doesn't shake. Sorry. I'm going to look at my ceiling for a minute. So 0.610 moles of, let's distracted. It's very hard to do this in front of while I'm talking and everything. So 0.610 moles of CuS. I'm still having troubles. Okay, so we're going to do a mole to mole ratio here. So I'm going to put 3 moles of CuS on the bottom, and I'm going to put 3 moles of CuNO3 on the top. And we're going to see the moles of CuS cancel out. Oh, and look at that. It's a 3/3 or a 1-to-1 ratio. So we don't really need to do any math on that one. You could do 0.610 times 3 and then divide by 3. That's fine, but you're still going to end up with 0.610 moles of the product, copper nitrate. 2. Okay, so that's the first one we did. So now I'm going to switch colors. I didn't leave myself a whole lot of space to write. So the next one is 1.4 moles, 1.40, I shouldn't have skipped the 0, moles of nitric acid, HNO3. And I'm going to do a mole to mole ratio. So I'm going to put HNO3 on the bottom, moles. And the HNO3 is 8 moles. And I'm going to put the product, the thing that we're looking for, on the top. So that's the 3 moles of copper nitrate, NO3, right? Did I do that right? Yep. And then, whoops, just an equal sign. So 1.40 times 3 divided by 8 is 0.525. 0.525 moles of copper nitrate. Okay, so then it asks how many moles of copper nitrate could be produced. They're not going to actually be produced because we haven't factored in our percent yield yet. So the right answer in this circumstance would be this one. The smaller amount is how much is going to get produced. So we would say that this one is the limiting reactant. The nitrate is the limiting reactant. The nitric acid is the limiting reactant. Okay, so now it says if the lab produces 0.50 moles of copper nitrate, what was the percent yield? So we had, instead of 0.525, we had 0.50. So let's just try that. So let's do 0.50 over 0.525. If I do that really quickly, 0.5 divided by 0.525 is 0.952. Actually, why don't I just do the multiply by 100 right now? Give me a second. So multiply that number by 100, and we would get 95.2, which actually there's only 2 sig figs here. So we'll say, oh my gosh, my handwriting's so sloppy, you guys. I'm really sorry. I got to stop writing so fast. 95%. There we go. So our percent yield would be 95% yield. Okay, let me know if you have any other questions, but that's it for now.